Hey, good morning, all you MRWC fans. This is Mr. Ainsworth again, and we are going to get into a Section 7 Part 3 review dealing with all activities from 7D1 all the way to 7F1. Just take a look at the review. Make sure you get Desmos set up, so make sure you log into your account. I've already done that. Go ahead and go up here to the top left of the screen here, select New Blank Graph, and then once you do that, go ahead and enter the title in, something appropriate, like the same thing, Section 7 Part 3 review. Okay, so do that. All right, get your Desmos set up, ready to rock. Get your Part 3 printed off from Canvas. And then once you go, get all that ready, let's get started. So I would get colors, do everything color-coded, do a good job, do your best. Again, this is to get you guys ready to review all the concepts from 71 all the way through, all the way through 7F1. All right, and that's it. There's more to Section 7 to that, but this is all we got through in this crazy year 2020 and 2021 during the pandemic. And again, my name is Mr. Ainsworth. Some of you guys are using these videos are not with me, and you're with some other instructor, so know that I'm helping you out this time. Okay, so given the graph here, determine the intervals where the function's either increasing, decreasing, constant, positive, negative. Colorize and annotate the graph, and to illustrate all the different characteristics that it may have. Okay, so here we go. Now, in increasing, you always want to look from left to right. Okay, always analyze the graph from left, all right, to right. Okay, just keep that in mind. So when I look at the function here, which is in red, okay, and this is the x-axis here and the y-axis here, and you get this, it looks like a polynomial function which has some zeros, has 3 zeros in fact, or x-intercepts, -4, -2, and 3. It's increasing on some intervals, and because it's going up to the upper left, or to the upper right, excuse me, from the lower left to the upper right, and then when it reaches its relative max, then it goes down and then back up again. And because of that, it's increasing and decreasing on some intervals. So let's highlight the some key points here. First of all, this point here, we'll call it point A, is called a relative max. It's at -3.082 roughly. So this point right here is -3.08, and it's called a relative max. And the max y value occurs when x is -3.082, and the relative max, or the y max, in this case, it's not asked, but I'm just going to go over that anyways because I'm going to be asking that on the test, is about 1.208, and it occurs at x equals -3.08. Okay, so it's increasing, okay, from negative infinity all the way up to this negative number here, -3.082 roughly. All right, it's increasing because it's going to the upper right, from lower left to upper right, and so it's increasing until it hits the relative max, and then it's decreasing. Okay, it's going down to the lower right. It's decreasing in this region here from -3.08 all the way to this number here, this relative min right here. This is called a relative min, and it occurs at 1.08. So this is 1.08. So between these two values right here, between A and B, we'll call B the relative min. All right. Between these two values, it's decreasing because it's going down, 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 and then it changes direction. It goes back up again. And so it's decreasing in this from A to B, from -3.08 all the way to 1.08, roughly, where the relative min occurs. And then it goes back up again to infinity. Okay, it keeps on increasing without bound. Okay, from 1.08 all the way to positive infinity. All right, so let's illustrate the intervals of increasing. So from negative infinity to -3.08. And again, I have to approximate these open intervals here. And the other open interval is from the relative min at point B, which occurs at 1.08. So 1.08 all the way to positive infinity. Okay, positive infinity. And those are the open intervals. Where it's increasing here because it's going to the upper right, and it's increasing from negative infinity to -3.0, and then from A to B, in between these two numbers, okay, on the x-axis here, I'm talking about, Okay, from in this interval here, it's going down in green. From A to B, it's going down to the lower right. It's decreasing. The y values are getting smaller and smaller and smaller until it hits the relative min, and then the y values increase from there without bound, okay, as x approaches infinity. So let's outline the interval where it's decreasing. So it's decreasing on the interval from negative 3.08 to the other x value where the relative min occurs, and that's at 1.08. Okay. Now it's not constant anywhere. Okay, so I'm going to say nowhere. Okay, there's no horizontal segments. So it's not constant anywhere because it doesn't flatten out anywhere. But it is positive and it is negative on certain intervals. Now, positive means that it's above the x-axis. Okay, negative meaning that it's below the x-axis. So we have to determine on what intervals does this occur. All right, so it's positive. Let's talk about where it's positive first. Between negative 4 and negative 2. So in this interval here. Okay, so from between the two x-intercepts here, from negative 4 to negative 2, and then it's also positive from 3 on to infinity. So from 3 to infinity, it's positive in this region right through here. Why? Because it's above the x-axis. Now, if it's below the x-axis, well, guess what? We call the function negative there because all the function values happen to be negative. All right, so it's negative in this region through here. So negative here from negative infinity to all the way to that x-intercept there at negative 4. So negative infinity to negative 4. And then on the other side, from negative 2 to positive 3, the other x-intercept, so in through here. Okay, it's negative there. Why? Because it's below the x-axis. So between these two x-intercepts, from negative 2 to positive 3. So negative 2 to positive 3. All right, it's below the x-axis. And that is just a little sample of what we did in the activity 71 and 72. Now the application of that is number 2. And we want to draw the function with all the following characteristics. Okay, so draw a possible function. Okay, so possible. So there's more than one answer possible here. So we've got to satisfy all these criteria right here. So we got x-intercepts at negative 2, all right, negative 1, and then at positive 1. Okay, those are the x-intercepts of the zeros of the function. Okay, so let's just check them off as we do it. Has a relative max at negative 2/10 and comma 1.1, so roughly negative 2/10. It'll be a little bit left of 0 there, and then up 1.1. So we've got 1.1 right about here. So right about here. So let's call this point A, and that's a max. So if it's a relative max, it's gotta, the function's kind of has to do something like this. It's got to go through the x-intercepts, and it's a relative max, so it's got to increase and then decrease to get a max. So I'm expecting something like that. And then a relative min, let's plot that. So let's call this point B. So negative 1.5, comma negative 3/10. So roughly, right about here, this is point B. And because of that, because it's a minimum, it's got to go down and then back up again. Okay, so the function's got to do something like that. It's increasing on negative 1.5 to 0.2. Okay, and so that's happening. Okay, so let's see here. So it's increasing on that interval, and it is. So I'm going to shade this interval in. So that's taken care of in green. So from negative 1.5 to negative 0.2, it's increasing because it's going up to the upper right. And it's decreasing. It's decreasing from negative infinity to negative 1.5. Okay, so if that's the case, maybe it does something like this. It's decreasing till negative 1.5. So it's going down, 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 down. Keeps going down until it hits that relative min. Okay, so it's decreasing there. And then from 2/10 to negative infinity. So from here, from point A is at 2/10, negative 2/10. it should be negative. Sorry about that. That's typo there. To negative infinity. So it's going to go down here, down here, down here, and then keep going down. All right, it's decreasing to negative infinity, so decreasing there. Okay, and then let's see, positive on negative infinity to 2. Let's see if I made that happen. So from negative infinity to negative 2, it's positive, meaning above. So it's above here. Okay, so it's positive here because it's above. That's good. From negative 1 to 1, it's positive here. That's good because it's above the x-axis. Okay, and negative meaning that's below the x-axis. From negative 2 to negative 1, that's true. Okay, so right here, it's negative there because it's below. And it's also negative here because from 1 to infinity, because it's below the x-axis there. So the function has to be something like that. And the curve, the shape of the curve could vary, but it's got to have all these attributes here. So there you go. That's one possible graph. All right. Number three. Okay, so let me see. So 1, 2. So number 1, 2. I forgot to number these things in my memory. So this is number 3. We'll just keep track from here. Okay, we got to go through all of this again, kind of like what we did on the last one here. So find the relative mins and max, and let's review everything that we just talked about. So this kind of puts in 7D2 with 7D1. 7D2, we talked about relative minimum and maximum. Okay, so increasing first. So it's going to be increasing all the way to this point right here. Okay, and this is a point is at negative 2, 9. So this we'll call this point A, and this one we'll call this one point B down here. And this is called a relative min. Excuse me, relative max. Point B is relative min because it's a low point. Relative max is a high point. High point, relative min, low point. That's how you think of it in simple terms. Okay, so it's increasing the point A, and then it decreases, and then it increases again. Okay, so it increasing from negative infinity all the way to this x value. Okay, to look where the intervals are, you look on the x-axis, not the y-axis. Okay, so you're looking at the x-coordinate, not the y-coordinate. So from negative infinity to negative 2, okay, there it's increasing. And then also right here from 0 to infinity, all right, it's going up again. This is the function. Okay, so from 0 to infinity, it's also increasing here too. Now it's decreasing in between. Okay, so from A to B it decreases. Why? Because it's going down. All right, the y values are getting smaller, not bigger. And the y values, if they go down, they get smaller, right? So from negative 2 to 0, it's decreasing. So from negative 2 to 0, it's decreasing. Going down. So going down. Increasing. Going up. It's that simple, believe it or not. It doesn't have any horizontal sections, so it's not constant anywhere, so I'm just going to put nowhere here. All right, no horizontal segments. Okay. Now it is positive to the right of negative 2 because it's above the x-axis. So above x-axis here, from negative 2 to infinity. Negative, it's below the x-axis, it's negative down here, and it's positive up here, right? So it's from negative infinity to negative 2, it's negative. So from negative infinity to negative 2, it's below the x-axis. Okay, the zeros, it only has 1 at negative 2 comma 0. Okay, this is an x-intercept here, or a 0 of the function, either one. It's an x-intercept of the graph, it's a 0 of the function, so there's the terminology for you. And the relative max, okay, occurs at x equals negative 2, and the y max, okay, its y value is 9. The relative min occurs at x is equal to 0, and the y minimum is equal to 1, okay? the y value there at that point, at the vertex, at the low point, it's called the relative minimum or local minimum, is at 1. Okay, so you look at the y values for the minimum maximum, where it occurs at is at the x values. All right, so make sure you understand that. That's 7D2. All right, let's go into the activities, E activities here. All right, so a little language first. So a function is an even function. Right here, an even function, if it is reflectional symmetry about the y-axis. So if you can reflect it across the y-axis, it's even. All right. Now it's odd if it has rotational symmetry of 180 degrees about the origin. And the origin I'm talking about 0, 0. Okay, so the algebraic interpretations though, so let's go over that too. So if it's even, you can take any point, okay, x comma y, okay, on the graph, and if it's even, you can transform it or you can reflect it over the y-axis and it becomes negative x comma y. Okay, if a point gets transformed that way, we call it even. Now if it's odd, okay, that's different. Okay, so any point x comma y, I think I put a comma b, but you can use a comma x comma y or a comma, it doesn't really matter. So if you transform it and if it's odd and you rotate it 180 degrees about the origin, okay, it becomes negative x comma negative y. I think in my lessons I went a comma b, it gets rotated or transformed to negative a comma negative b, and then this one, if I used a comma b, the a comma b gets transformed to negative a comma b. So if that's what I used in my lesson, it's the same thing, just different letters. Okay, so here we go. Let's apply what's going on. So I can see that this first graph, this is number 1 here. And let me see, this is problem number 4. So we'll call this problem 4 here. Okay, so graph 1, the first graph, first, second, and third. So graph number 1, graph number 2, and then graph number 3 here. Okay, so graph number 1 here, I can see that it has rotational symmetry about what's called the origin. Okay, this is called the origin right here. And if I rotate, and you could do this with a piece of paper here, you trace just the function in quadrant 1. Okay, we went over this in class, and also I go over this in my videos here. But if you trace this function here, I'll make it red right here. So if you trace and use some patty paper here or wax paper, oops, gotta spell this right, patty paper, okay, or wax paper in the kitchen, either one will suffice because it's basically the same thing. But if you trace this portion of the function in quadrant 1, and then you rotate this point call it 2 comma 8, we'll call this point A, and you rotate it 180 degrees, okay, that means if you line up the axes, you also trace the axes here, the x and y axes, and then you rotate it not just 90 degrees, okay, but another 90 degrees. You rotate it 180 degrees, then A will go to A prime, okay, and A 2 comma 8 will overlap negative 2 comma negative 8. And because of that, when you see a point get transformed to its opposite, negative 2 comma negative 8, it satisfies this right here. So A comma B gets transformed to its opposite of A, comma the opposite of B. When that happens, the function is called odd because it has rotational symmetry about the origin. So this indicates that you have an odd function. Okay, because it has rotational symmetry. Rotational symmetry of 180 degrees about the origin. Okay, so when you see that, and you can do this with trace paper, you trace again the axes and the function in quadrant 1, rotate your paper by putting your finger or your pencil tip actually on the origin, and just rotate your paper. Rotate it basically 2 multiples of 90 degrees, and so that it gets rotated, and this piece right here in red that I traced will overlap this portion down here in green. It will basically overlap once you rotate the paper about the origin. Just put your pencil at the origin, rotate the paper, boom, it will overlap itself. Pretty cool. And if you stop the video and if you haven't got your trace paper out from prior activities, you should do that. Because that's how you see it. That's what we do in class. Okay. Now the graph number 2 got a parabola here, and this parabola here does not have rotational symmetry about the origin. It's actually a reflection across the y-axis. Okay, so this point A will get reflected to A prime. Okay, it's reflected, okay, over the y-axis. And whenever you notice this, you call this function even. Okay, so algebraically speaking, 2, 4 gets transformed to negative 2 comma 4. That's the same thing as taking any point A comma B, and if it gets reflected to the opposite of A comma B, which happened right here, the opposite of 2 is negative 2, and B doesn't change, this indicates that you have a reflection, okay, over the y-axis, and any graph that has a reflectional symmetry over the y-axis is called an even function. Okay, now if it doesn't have the rotational symmetry about the origin of 180 degrees, and if it's not a reflection over the y-axis, then it's neither, it has neither symmetry here. And this graph number 3 is like that. Okay, so if you take a point on the graph, let me pick a point like this one. This is 2 comma 3. We call this A. It's at 2 comma 3. Just go 2 units right, 3 up. Now, if this was even function, then A would get it'd get reflected over here to A prime. And notice that there's no graph there. The graph isn't there. Okay. Notice that the line of symmetry is not the y-axis. It's actually going through x equals 1. This is the line of symmetry here. Line of symmetry. It happens to be x equals 1, not x equals 0, the y-axis there. And so it does not have y-axis symmetry. So we can say it does not have y-axis symmetry. So because of that, I can say it's not even. Okay, now if you take 2 comma 3 and you apply the definition of odd to it, okay, then it should get transformed to the opposite of A comma opposite of B. And the opposite of A would be negative 2, and the opposite of negative 3 would be positive 3. So negative 2 comma 3 would be that's positive 3, I'm sorry. So 2 comma 3 would get transformed to negative 2 comma negative 3, which would be down here in quadrant 3. We'll call this A double prime here. And of course the graph's not there, right? So this graph does not have, okay, rotational symmetry. So does not have rotational symmetry about the origin. And because of that, it's not odd. So it's neither, okay guys? It's neither odd nor even, okay? Because it doesn't have those kind of symmetries there. So you guys have to be able to identify whether it's odd or even just by looking at the graph. Okay, now once you understand that, then you can do this one here. In this activity 72, you complete the graph by making it either odd or even. By given half the graph, create an even or odd function by understanding the symmetry. So to make graph f even, you just need to make it symmetric about the y-axis. Okay, well, let's make that happen. So here's the y-axis here. Okay, it's got to be symmetric about this vertical axis here. And so we have to reflect it across. And if you want to use trace paper, you can, or you can just simply use the coordinates. So let's use the coordinates. So B is at negative 2 comma 4. So negative 2 comma 4. Notice that it's 2 units to the left of the axis. So B prime has to be 2 units to the right at 2 comma 4. C prime, or C, is at negative 5 comma 3. So if you reflect that across the y-axis, you go at 5 comma 3. So you got to go right 5 up 3. And that's where C prime is. And then D is at negative 6 comma 1. So if it's even, any point A comma B gets transformed or reflected in this case to negative A comma B. So you take the opposite of A comma B, whatever B is. Or you can use the other variables. If you like X and Y, then X comma Y gets transformed to negative X comma Y. So just take the opposite of x and then the same y value. Opposite of negative 6 is 6, so 6 comma 1, which would be point D. And then you form the graph. Okay, so you can just draw that graph here. Draw better than that. Okay, there we go. Okay, and so notice that B gets reflected, C gets reflected, D gets reflected. So it's reflection over the y-axis. Okay? That's all you do. And then if you want to check it, just fold the paper along the y-axis, okay? And all these points should overlap. That's what symmetry is all about, okay? If you know where the line of symmetry is, guys, then just make it happen. All right, now if you want to make it odd, okay, again, to make things odd, you can do it algebraically, which might be easier in the beginning, or you can use trace paper. But remember, if it's odd, then every point gets transformed to the opposite coordinates. So x comma y gets transformed to negative x comma negative y, or a comma b gets transformed to negative a comma negative b. Okay, you got to take the opposite of both coordinates. Okay, opposite of both coordinates. Okay, so let's do that. So any point x comma y on the graph gets transformed to the opposite of x comma opposite of y. Okay, okay. Or you can simply trace this with trace paper, rotate it 180 degrees by putting your pencil at the origin right here and just rotating your paper 180 degrees, and then you'll see where the function should be. All right, but if you want to use coordinates, then okay, let's do it. So point B, again, this is at negative 2, 4, so negative 2, 4. Okay, so negative 2 comma 4, this is point B, gets transformed. You got to take the opposite of both, so B prime should be at 2 comma negative 4. So you go right 2 down 4, so there's B prime. C is at negative 5, 3, negative 5 comma 3, and it gets transformed to C prime. You got to take the opposite of both, so it's 5 comma negative 3, so go right 5 down 3. There's C prime, and then D is negative 6, 1, negative 6, 1 here. So D is negative 6 comma 1, and it gets transformed. You got to take to D prime, got to take the opposite of both coordinates here, and 6, 6, negative 1. So 6, negative 1 is here, and there's where D prime is. And so you just go ahead and draw the function now. Okay, so notice that if you rotate B 180 degrees, okay, look at this, 180 degrees rotation counterclockwise, or you can go the other way, clockwise, it doesn't matter. Okay, B would transform to B prime, and then again C would get transformed to C prime, and D would get rotated to D prime, and so on. 180 degrees about the origin. Again, this is the origin here, which is at 0 comma 0. All right, that's activity 7E2. All right, let me see, that was number 4, this was number 5. Okay, number 6. Okay, so this was in activity 7E3, and we're going to use Desmos to help us recall all this information here. Okay, so this is where we want to start using Desmos. All right, so what we're going to do is we're going to do a split screen here. All right, so get your Desmos ready to rock and roll. Okay, so let's enter in the functions. Okay, you enter in y equals sine x, and you'll notice that we don't have symmetry about the y-axis, so this is not even. Okay, so I'm going to wipe that out. So it's not even, not symmetric about the y-axis here, not symmetric about y-axis, so it's not even. Okay, and then you notice that pi halves comma 1, if you rotate it 180 degrees, it goes to negative pi halves comma negative 1. Notice the coordinates are the same but opposite in sign. They're the same but opposite in sign, and that right there is an indication that it's odd. Okay, so the sine function's odd. You got to remember that. Okie dokie. So this is odd. And let's check out the other ones. Cosine function. So type in cosine. Again, you guys should be doing this and saving your work as you go. You do all the typing because you're going to submit your Desmos work as like we always do. Okay, so you're used to that, you guys. For anybody that's not in my class, that's what we do in Ainsworth's class. We do everything in Desmos. We print a PDF and we do send everything digitally into Canvas. Okay. All right, cosine. Let's switch functions here. So we need cosine. There we go. So type that in. So notice that we have y-axis symmetry here, so it's even. Okay, because pi halves comma 0 gets reflected to negative pi halves comma 0, so this one's even, not odd. So it's even here. Okay. Uh-oh, I just put that in the wrong place. Okay. G of x equals x squared, so we need the x squared function. Okay, that's your famous parabola. Okay, that's even as well because it has y-axis symmetry. And then x cubed. Okay, once again, you just graph the function here. Notice here's the origin, 0, 0. And if you take a point, let's say like 1, 1 on the graph, let me put this in. Watch this. This is kind of cool. I'm going to type in 1, 1. So 1, 1. Okay, let's label that. There's 1, 1. And if you take the opposite of both of those coordinates, all right, it should be on the graph because it's odd. Okay, it has rotational symmetry about the origin. So if I rotated the graph in quadrant 1 180 degrees, the portion of the graph in quadrant 1 would overlap the portion of the graph in quadrant 3 because that's what rotational symmetry is all about. And so let's add in another point here. Okay, so -1, -1. All right. And so notice that happens, okay? So if you rotate about the origin 180 degrees, 1, 1 would overlap -1, -1. So this function is odd. Okay, so let's go back to the lesson here. All right, so we have an odd function here. So we have 4 functions to play with here. We know they're even or odd just by using Desmos here. So use Desmos. Okay, to determine all that, I wrote it up here. Okay, so said it twice. Okay, so let's answer the following questions here. So if false, give a counterexample using the given functions. Okay, it's the product of 2 even functions. Okay, product meaning times. If you multiply 2 even functions together, do you get an odd function? Okay, so let's take some even functions. Let's take x squared and cosine x, and let's multiply them together. All right, so we want to use Desmos to play with this idea. All right, so we want cosine x, and we want x squared, 2 even functions. So product of 2 even times an even, is it odd? Okay, so let's do that. So where is that function? Oh, here it is right here. So x squared's even, cosine's even, and look at this right here. Okay, you have the product, you have the product of 2 even functions, and it has y-axis symmetry. All right, so it is not an odd function. All right, so this is false. Okay, and so we have to give a counterexample. So x squared times cosine x. All right, so this is an even times another even. All right, gives you an even function. Okay, has y-axis symmetry. Y-axis symmetry. Okay, let me just grab this in here. Okay, so you can see it right here in this little picture right here. I'm using Desmos here. So it has y-axis symmetry. You can tell because it's a reflection. Like this point right here, call it A, gets reflected to A prime. Okay, look at that. This point B, I don't know where it is, but it gets reflected B prime. All right, it gets reflected across the y-axis. That's the y-axis right here. So this is an even function. Any function that looks like this has y-axis symmetry is even. So an even function times an even function is not odd. Okay, so I said false, and I gave a counterexample. I picked 2 even functions, and I got an even function by looking at Desmos. Okay, now is a sum of two even functions an odd function? All right, so I can't use this prior example here. I got to add the functions. I don't, sum means you add, not multiply. So make sure you do the right thing. You got to know the vocabulary here. So this function's not a good example to look at here. So let's add two functions. Oh, this is right here. So x squared and cosine x are both even. So let's take a look at this right here. And look at that. It has y-axis symmetry. So an even plus an even is not odd. Okay, so this is false. Okay, false. An even, all right, plus an even is equal to an even function. Okay, x squared plus cosine x, all right, it has y-axis symmetry. Okay, so here is an example. So let me bring this into. There we go. Okay, so obviously this one here has y-axis symmetry here. So A gets reflected over here to A prime and has y-axis symmetry. So it's even. So an even plus an even is not odd. So you just play with the functions here. So is the product of an odd and even an even? I don't know. Let's pick some functions. Okay, so we have to pick the functions above here. We have to pick an odd and an even. Okay, so let's deselect this. Okay, so sine x is odd, okay, and product means multiply, so we got to multiply these together. So let's try sine x here for an odd, and let's try an even. Well, you can pick x squared, or you can pick cosine x. It doesn't really matter. So sine x is odd, and then cosine x is even. So if I use these two, so this is an odd and an even. What do we get? So do I have this one in here? No, I have to go ahead and add an expression here. So sine x here we go. Let's just type in sine x. All right, let's multiply it by cosine x. Look at this is why I love Desmos here. And check this out. Look at this. All right. So here we go. And look at this, 1 comma 1 gets rotated to 1, negative 1 comma negative 1. We talked about that before. That's an odd function right here. So if you take an odd times an even, you don't get an even, guys. All right, so this is false. Okay. False and odd, all right, times an even. Function, not number, okay, is equal to not an even. This is odd. Okay. Then my example is that sine x is my odd one, cosine x is my even one. There's my counterexample, and my graph is my counterexample. All right, because this has rotational symmetry. Oops. Sorry. There we go. There's my counterexample. All right, this has rotational symmetry right here. So if we call this point A, gets transformed to A prime right here. And again, this is a rotation of 180 degrees. It has rotational symmetry of 180 degrees about the origin. There's my counterexample. Okay, so you're going to be using Desmos to explore and to find counterexamples. Okay, so kind of cool. All right. Let's see, so we're just applying skills. Okay, so let's go further here. That's 73, let's jump into 74. Now 74, now we're getting more algebraic and more symbolic, okay? And this activity here, all right, we want to figure out whether the following functions are even, odd, or neither. We want to verify, look at this, we want to verify your claim by using symbolic definition. Ooh. Okay, and then we're going to use Desmos to verify graphically. Okay, so step 1, step 2, step 3. Okay, and this one happens to be number 7. I forgot to put the numbers in. Okay, so problem number 7. All right, so we know from prior lessons here that if a function's even, then if you substitute negative x in for x and you get the original function, it's even. Okay, why is that? Well, let's say, so this right here, here's the y-axis, okay, and notice that A gets reflected over the y-axis to A prime, okay, so therefore it's even. We know that. But notice that the function value here, this distance right here, okay, we call that f of x. It's a distance, f of x, is actually equal to, it's the same height or same distance as f of negative x. So these two things are equal, okay? So notice that f of negative x equals f of x. Ooh, they're equal. Equal height. How about that? Okay, now that's if it's even. Now, if it's odd, that doesn't happen. So here, let's say A gets rotated 180 degrees. Okay, rotated 180 degrees about this point 0, 0 here. Okay, a rotation of 180 degrees to A prime. And that's only the case if f of negative x, okay, equals the opposite of f of x. Okay, so that word's like this distance here, which is f of negative x, it's equal to the opposite of f of x, okay? Because this number is negative and this number is positive, so you got to take the opposite of it. But they're the same values, but opposite in sign, okay? Same values, opposite in sign. That's what this definition is here, okay? And then even this definition here. Okay, so here we go. So let's do the algebraic part. Okay, so all we do is substitute negative x in for x and see what happens. Okay, so this is what you do. And if you do that, do you get f of x, the original function? Okay, this is the original function. Okay, or do you get the opposite of the original function? What happens? So you just explore, and whatever the end result is will tell you whether you have an odd or an even function. But you got to start with this. Okay, here we go. So this is where it gets a little abstract here, because now we're dealing with the symbolic definitions, and this is where students typically break down and have a tough time because it's all symbolic and algebraic. So if you have to review and listen to this a couple times, then do it, because this is not easy in the beginning. Okay, so I'm going to put this in red. Okay, so we have to substitute negative x in for x and see what happens. Okay, so here we go. So instead of y, I should have put f of x here, so I'm going to change this right here. So f of x equals e to the absolute value of x plus x squared plus x. Woo! Okay, so we start off with f of negative x. Here's my substitution. So I have to take negative x and I have to substitute it wherever I see x. So this f of negative x is equal to e to the absolute value of negative x, because I got to substitute negative x in there, plus negative x squared, because this is a squaring function, all right, plus 6. And now I got to simplify it, okay? Now the absolute value of negative x is just the same as x, or the absolute value of x, okay? So because when you take the absolute value of negative, it's going to be positive. So this is the same thing. And whatever you square, like let me do a little side thing here. So negative x squared is the same thing as negative x times negative x. Well, guess what? That is just x squared. So when you square a negative, you just get a positive. So this simplifies just x squared, and 6 is constant. It's called a constant. Doesn't change. And notice that this right here is the original function, called f of x. So notice that these two things are equal. F of negative x equals f of x. And that, my friends, is the definition of even. So this is an even function by definition. Okay? This is basically a formal proof of what if a function is actually even. Now, if you want to verify it with Desmos, that's verifying graphically. That's a little bit different. Okay, so verify graphically using Desmos. Here we go. So that's why you see Ainsworth always go two column format here, meaning split screen side by side, and I have Desmos on the right, and you guys do the work on the left. Okay, and we do all the action on the left. So we got to put this function in, of course, right? And I think I did somewhere. So here it is. Okay, so let's check to see if it's right. It's right. So just go ahead and type that in. And I got to take off my previous one. So deselect the previous function so you don't see multiple things. Okay, and notice here, look at this crazy function here. Okay, notice that it has y-axis symmetry here, and therefore it's even. So let's capture this right here. Okay, so there's the graph. So you can see it right there. And notice it has y-axis symmetry right here. Here's the y-axis. Okay, the y-axis right there. And it has symmetry across that y-axis. So A gets transformed to A prime. All right, so it's symmetric about y-axis. Okay, and because of that, it has to be an even function because that's what we've been talking about. Okay, so we want to do it algebraically, and then we back everything up graphically using Desmos. Okay, because in mathematics things have to make sense, and that's the beauty of mathematics. Because if it doesn't make sense two different ways, then obviously you've done something wrong. All right, so we always do it symbolically first, do the algebra here, and then back it up with a nice graphing tool called Desmos. Okay, all right. Now, let's take a look at this one right here. Let's do symbolic. Okay. So we want to substitute negative x in for x and see what happens. So sub negative x in for x and see what happens. So that's why I always start off with f of negative x, because you have to substitute a negative x and see what happens. So I got to substitute in two locations here and then simplify. Now, what is cosine of negative x? What is that? Is cosine even or is it odd? And let me see. Did we do this already? Okay, we analyzed what happens with sine x, but we did. We analyzed what happened with cosine x. Now, cosine x is even. Okay, and we did that graphically. Now, because cosine x is even, because of that, we know something right here. So let me do a little something on the side. Okay, so we'll do a little side something here. So note or recall. Okay, so cosine x, all right, is even. Okay, so according to our definition, right up here, if it's even, f of negative x equals f of x. So if f of x equals cosine x, that means f of negative x, okay, is equal to, all right, f of x. If it's even, that's by definition, which means, okay, cosine of negative x is equal to cosine x, because by definition, it's equal to the original function. And if you don't believe me, well, let's go back to Desmos. If you type in, let me just type both functions in here. Let me go back to the previous function here. So when in doubt, you do this. Okay, there's cosine function right here. Here's the cosine function. Now, if I type in cosine of negative x, it should be the same thing. So let's do that. Y is equal to cosine of negative x. Okay, and notice that if I turn off the first function, I get purple function. If I turn on the red function, it's the same thing. We don't see two graphs, we only see one, because they are the same thing. Why? Because it's even. It has his reflectional symmetry about the y-axis. All right, so pi halves comma 0 gets reflected over to negative pi halves comma 0 and back and forth. Okay, these graphs are the same. All right, so because of that, I know that this right up here, this is actually equal to just cosine of x. Negative x is just negative x. I'm going to rewrite this a little bit here. I'm going to pull out the negative and just write it like this. The reason why is because cosine x over x, notice that it's the original function. So if that's the original function, I get negative x. And so you'll notice here, if you just look at these are all equal. All these expressions are equal, okay? So this right here, f of negative x, is actually equal to negative f of x, all right? And that is the definition of odd, okay? And so this right here, this tells me, my conclusion says, is that f of x must be an odd function. So f of x is an odd, all right, function, because it satisfies this definition of what it means to be odd. Now, if you want to see it graphically, well, you type it in, right? So let's see if I typed it in already. Here we go. All right, so you got to turn off the previous function, so turn them off. And then you got to turn on the new one here, cosine x over x. And notice right here that it has 180 degree rotation about the x-axis. So pi halves comma 0 gets, if you rotate it 180 degrees, it'll end up over here at negative pi halves comma 0. All right, so as a graph, it definitely is odd, all right, because it has rotational symmetry about the origin. So let me grab this one here and bring it in. There you go. So that's what it looks like, basically. All right, look at that. So any graph that has rotational symmetry about the origin, like A here gets reflected to A prime, okay, gets rotated 180 degrees. So if you rotate it 180 degrees about the origin, which is right there in the middle, okay, you have what's called an odd function. And I know I keep repeating myself, but you know, when you're learning and you're trying to understand this stuff, hey, repetition is important. Guaranteed. All right, next one. Okay, in this section right here, on number 7 here, we have to analyze 3 functions. So let's go to the third one here. F of x equals sine of 5x. So once again, I do the same thing. I want to substitute. Excuse me for a second, I got a little... let me reboot my program here. So I want to substitute, oops, I want to do this in red. Negative x in for x. You do this every single time. Notice that I keep on repeating myself here. You substitute negative x in for x and see what happens. That's the standard procedure when you do this algebraic thing. So f of negative x is equal to the sine of 5 times negative x. Again, you have to substitute in right where you see x. You gotta, so if I want to substitute in negative x, okay, right here, I got to substitute wherever I see x. Then I multiply 5 times negative x, which is obviously negative 5x. All right, so I get the sine of negative 5x. All right, but we said above here, let me see, where did we say it? We said that sine is odd. Okay, sine is an odd function. We determined that earlier. And if it's odd, well, that means that f of negative x equals negative f of x. Okay, let's apply the odd definition. Okay, so this is odd. We know that. So this is negative of sine of f of x because it's odd. That's the reason why. And notice that this right here is nothing more than f of x. So this is negative of f of x. And so if I bring this down right here, you'll see that f of negative x is actually equal to negative f of x, which is the definition of an odd function. Okay, so this must be odd. Okay, so let's grab the function in Desmos and let's, whoops, what happened here? Give me a second here, guys. Okay, so deselect the previous one. Make sure you save your work all the time. All right, so we got to do this one here. Let's modify it. So the sine of 5x here. Let's turn the function on. Okay, and notice that pi halves comma 0 right here at, or excuse me, pi tenths comma 1. If you rotate it 180 degrees, you get negative pi tenths comma negative 1. And that, my friends, is a definition of an odd function because it has rotational symmetry about the origin, rotational symmetry of rotational symmetry of 180 degrees. So let's bring this function in here so we can take a look at it. Okay, so we're looking at the function now, and as I was saying here, let's say a here at pi tenths comma 1 gets rotated, all right, to this point down here, call it a prime. So x comma y, okay, becomes negative x comma negative y. So whenever a point on the graph gets transformed to the opposite coordinates, all right, that's a definition of odd, okay? This is an odd function because it has rotational symmetry, 180 degrees, rotational symmetry, okay, about 0, 0, and that point's called the origin right here. Okay. All right, so that's a little taste of how you show symbolically that a function's either odd or even, and then how you validate it with Desmos. Again, in my class, we use Desmos a lot because we've once you get trained in that, man, it's just so easy and so awesome to use. There's so many things it can do, and it's free to everybody. Okay, that and GeoGebra and a few other programs are probably the best programs to use on the web. All right, let's get into the last section here, where we prove odd and even functions symbolically. Okay, and as I said before, if a function's even, okay, f of x is equal to negative f of x. All right, if a function, is equal to f of x, even, that's this portion up here. Okay, actually, let's not do that. Let's just highlight it. So f of negative x equals f of x, the original function, if it's even. And if it's odd, well, that's different. If it's odd, okay, then f of negative x, well, is equal to the opposite of the function, which we say negative f of x. Okay. All right, so let's apply these definitions, and let's see what we can do. This is going back to 75. All right, suppose f and g are odd. So we say let f of x and g of x be odd. That's important. Okay, now if that's the case, that means f of negative x, okay, equals, okay, apply the odd definition here, okay, equals negative f of x by definition of odd. It also means that g of negative x is equal to negative g of x. Okay, why? Because it's odd. Okay, this is what we start with. I haven't even started proving yet. We want to show or prove that the product, okay, if you multiply f and g together, it's even. Okay, so let's call the product p of x. Okay, so let p of x equal the product of the two. So f of x times g of x. Okay, we have to multiply them together. So notice that I'm doing that. And we have to show that it's even. That means I have to substitute in, so sub in negative x, in for x, all right, and show, all right, that p of negative x is actually just equal to the original function, p of x. That's what we have to show. So here's now the proof, okay, so let's get started. So you start off with substituting in negative x. So you start it with p of negative x, okay? There's my little substitution right here. We always substitute in negative x and see what happens. If we get the original function, it's even. If it's the opposite of the function, then it's odd. And if we don't have either one of the two, then it's neither even nor odd. Okay, so here we go. So I'm going to substitute in negative x. So once again, I put negative x here, here, and here. So f of negative x times g of negative x. Well, what does that equal to? So, well, I know in the beginning over here that f and g are odd. Because of that, I know, okay, by definition, right, this right here is all by definition of odd, okay, of odd. That f of negative x equals negative f of x, okay. All right, so I'm going to substitute that in. So negative f of x. And I know that this portion right here is equal to negative g of x by definition, because that's what I started with. I assume that f and g are odd. So it's important that you write this down here in your proof. Because if you don't know what your assumptions mean, all right, these are called assumptions. You get to, or given, either one. Assumptions or given. If you don't know that you're given two odd functions, then you can't do anything in your proof. Okay, and now notice that I'm dealing with two odd numbers, or excuse me, negative numbers here. A negative times a negative is a positive, so I'm going to put a plus sign here to emphasize that. All right, and then I get a negative times a negative is a positive, okay, f of x times g of x. All right, and notice that right there by definition is p of x. Look up here in the beginning. P of x is defined to be f times g, or f of x times g of x. So that's equal to the original function called p of x, the product function, okay, because I'm dealing with a product. So notice that I'm going to notice this right here. Just going to bring this down. So p of negative x equals p of x, and that is the definition of even. This means even. And then I'm done with the proof. Okay? QED, quod eris demonstratum. Quod eris demonstratum. Demonstratum, I think it's right. It's Latin, okay? And so if you want to know what that means, that which to be demonstrated, or if you don't believe me, go ahead and research that. Type in QED and into the browser there and check that. That's a very famous thing that the Greeks used to put at the end of their proofs when they prove something, okay? And we are done with the proof right here, okay? So QED. All right. Now, let's take a look at another proof, all right? Because it takes more than one example to get good, all right? So let's try this. All right. Suppose f and g are odd again. So I am going to bring this down again. So you start off with what your assumptions are. What are you given? Okay, so you say, okay, let f and g, all right, be odd. What does that mean? Okay, odd is important. That means that f of negative x is equal to negative f of x. That's what it means to be odd. G of negative x equals negative g of x. That's what it means to be odd. Okay, you start off with that. These are the assumptions. Just like I did the previous one here above. Notice the similarity. I'm given two odd functions here, and we want to show that the sum this time, sum means you add them, that f plus g is also odd. So an odd plus an odd is giving you an odd. Well, let's check that out. Okay, so I'm going to use the s as our, instead of p for product function, I'm going to use s for sum function. So s of x is equal to f of x plus, okay, sum plus g of x. Okay, and I have to do what I did before. Let's look above here. I want to substitute a negative x in for x. So I sub negative x in for x and show that f plus g is odd. Show means prove. And show f plus g is odd. So let's do that. And to do that, I have to show that f plus g is, so, well, I'm going to, actually, instead of f plus g, I use s. Okay, so s of x. Okay, so f of x, s of x is odd. Okay, and that means I have to show that s of negative x is equal to negative s of x. I'm sorry, I just had to think for a second there. So odd means that if you substitute negative x, you get the opposite of the original function. Okay, that's what the negative sign means, is the opposite of the original. Opposite of the original function. Okay, that's what it means to symbolically. So what do we get? So let's work on this here. So here we go. So I'm going to substitute in negative x right here, here, and here, and go with the flow. All right, so s of negative x is equal to f of negative x plus g of negative x. You got to substitute negative x everywhere. Well, by definition, f of negative x is equal to negative f of x. By definition, g of negative x over here on the left is equal to negative of g of x, opposite of the original function, because they're both odd. That's what it means, okay? And notice that they're both negative, so I'm going to factor out a negative here. All right, just factor it out, okay? And if you do that, if you factor out a negative, you get the opposite of f of x plus g of x. And by the way, this part right here, what is this? What's f plus g called? Well, it's called s of x, right? So what do I get? I get negative of s of x. So I'm just going to bring this down so you can see the equality here. So s of negative x is equal to the opposite of f of x, okay? This is the definition of odd, and I had to show that it's odd. And again, this is a formal proof, symbolic formal proof of showing that something's odd, and this takes some getting used to. So the fifth activity, this is 7E5, I think. Yeah, 7E5. This takes some getting used to, and this will take practice. Now, when I was in college at Cal Poly Pomona, their proofs obviously a lot harder than this. When I was, proving calculus theorems and everything, and doing epsilon delta proofs and all that. And when doing that, I'd have to go through the instructor's proofs and practice when I was at home, for hours and hours by repeating and practicing until the light bulb went on, until I started getting this. So you might have to listen to this to a few times and then actually practice this, actually write it all out like I'm doing here multiple times until you can do it on your own, because this stuff in the beginning is not easy. All right, so keep that in mind. All right, and in this course here, in this crazy 2021, we didn't get past 7F1, so we're going to end it with this one here. This is I think the 8th one here. Let me see, so, see, this is number 7, so this is number 8. I forgot to number this thing, so number 8, okay, and then this is number 9. Okay. So number 9. So our goal here in this one is you describe the end behavior. Okay. So end behavior is like as x approaches infinity, y approaches what? Okay. As x approaches a negative infinity, y approaches what? Okay. You have to determine the end behavior. What happens to the far right? Okay. When you're going towards infinity, you're going to the right. Okay, and what happens to the far left? If you go to negative infinity, that means you're going to the far left. I probably should have started off with this one, but who cares? All right, and so we want to discuss the end behavior and see if there's any asymptotes of the function symbolically. Do this symbolically. Okay, how do you do that? So write it symbolically instead of in words. Okay, so the x-axis is here. So negative infinity is to the left and positive infinity is to the right. And this middle dark line here, this is the y-axis. Okay, so we got this parabola function here. This is our function here. And notice that if you go to as you go left here, okay, as you cruise to the left, as x goes to negative infinity, all right, negative infinity, as you go to the left, the function goes down, okay, and it goes down and down, and the y values decrease without bounds. So as x goes to negative infinity, comma, y approaches negative infinity, because this goes down without bound. Okay, it goes downward or down without bound. And that's a fancy way of saying it never stops, guys. Okay, it goes down to negative infinity. That's what parabolas do. So as x gets more and more negative, y gets more and more negative. Now on the other side of the fence here, okay, when you go to positive infinity, when you go into the right, so as x approaches positive infinity, all right, the y values go down on this side as well, okay? And they also go down to negative infinity. So we say y approaches negative infinity, which is a fancy way of saying that it goes downward, okay, without bound. Okay, it gets increasingly more negative, is what I'm saying. That's graph number 1. Now, graph number 2, this is a different case, all right? This probably goes up, all right? So let's analyze what happens to when you go to the right, and let's analyze what happens when you go to the left. Okay, so right here, so as x approaches negative infinity, the function goes up without bound, and it goes up to positive infinity. So y approaches positive infinity as x approaches negative infinity. And on the right-hand side, as x approaches positive infinity going to the right, okay, notice that the function goes up to the right. It goes upward without bound to positive infinity. So the y values approach infinity as well. Okay, it goes up without bound. It goes up on both sides. Both sides increase without bound. Okay, and that's what parabolas either open up or down in the form of y equals f of x. There are parabolas that open up left and right, but we're not analyzing those at this point. Okay, that's for another time. All right, on the third graph down here, as you approach negative infinity to the left, the graph decreases without bound. Okay, so we can say as x approaches negative infinity, y approaches negative infinity. Okay, and then on the right hand side, as you go to the right towards positive infinity, and the graph increases without bound. Okay, so it goes to positive infinity. So I can say that as x goes to positive infinity, comma, y approaches positive infinity. This is symbolic, okay? I'm not writing it in words this time. I'm writing it using symbols. But you can go back to 7F1 and take a look at this. And then on this next one here, there happens to be a horizontal asymptote, okay, at y equals 0. HA is horizontal asymptote. All right, so when you go to the left here, notice that the function oscillates. So oscillates, oops. Okay, oscillates, goes back and forth, and it approaches the x-axis here, which happens to be y equals 0. So I can say that as x approaches negative infinity, as you go to the left here, this direction, okay, the y approaches 0. Why? Because it gets closer and closer to the y-axis, and which has a y coordinate of 0. Same thing happens on the right, okay, as x approaches positive infinity going to the right, y oscillates up and down over the x-axis here, so y approaches 0 in this case. All right, now let's take a look at functions. This is number 10. So given a function, instead of graph, given a function, describe the end behavior. Okay, and use Desmos. So let's use it. So let's screen it here, and let's use Desmos. So let's take a look at cosine over x function, which happens to be right here. And let's take a look at it here. And notice that it oscillates right here. Look at this. Let me grab a point on the graph here. It goes below, above, below, above. But look at the function values. When let me zoom out here. Look at it oscillates. It goes up and above and below the x-axis here. So as you go further right, it kind of flattens out, and y approaches 0 again. How about that? And the same thing when you go to the left, as x approaches negative infinity here. As you go to the left. Okay, there's a lot of x-intercepts here because it keeps on going above and below, and so there's an infinite number of x-intercepts here on this function, which is a very unique function. You'll study more of this in calculus. Okay, so so on this one here, let's screenshot this guy. Let's bring this guy in. Oops, sorry. Let's try that again. Excuse me. Okay, here we go. So let's screenshot this and let's bring this guy in. You can see how it approximates, or it oscillates above and below the x-axis, which means that it y approaches 0 on both sides of the fence. Okay, on both sides. You know what I'm going to do? Let me just do something real quick here. And do something cool with technology here. So this is number 1 here, but I need change this here. Give me a second here, guys. We just change the organization here for a second. Forgot to do this. Okay. There we go. Okay, so there's the first graph. And so I can say down this one here that as x approaches negative infinity, y approaches 0. That's looking at this part of the graph. And then as x approaches positive infinity to the right, positive infinities to the right, y also approaches 0 on the right. So that's looking at this portion of the graph over here. Now we need some graphs for the other two, so let's get some graphs for the other two. So type them in, and like I said, save all your work here because you guys are going to be submitting this in Canvas. Okay, you always submit your Desmos work with your written work. At least you do in my class. Okay. Okay, so here we go. We've got a 4th degree function here. And notice it keeps going upward on the upper right and to the upper left. And this is a 4th degree because 2nd degree times 2nd degree will give you a 4th degree function. Okay, so let's, yeah, there we go. Change the look of it here. So let me grab this function here. Okay, so notice that as you go to the far left, the graph goes up. If you go to the far right, the graph goes up. And so whether you go to the left or to the right, we have this similar type of behavior here. Y increases without bound. Okay, so if you go to negative infinity, the y values increase, okay, and go to positive infinity. If you go to the right, the function increases without bound to positive infinity, so it increases without bound on both sides of the fence. So we can say as x approaches negative infinity, I'm looking on the left side here, y approaches positive infinity, and then on the right side, as x approaches positive infinity to the right, y approaches positive infinity, because it goes up on both sides, you guys. All right, so this function is totally different than the previous one. All right, and then the last one here, let's take a look at it. Should be this one here, I think. Yeah, okay. So let's adjust the zoom angle here. Okay, here we go. So, let's turn these off. Okay, so this one here, let's select this here and screenshot, and let's bring this one in. So notice on this one, okay, so on this one, as you go to negative infinity here, so negative infinity on the left, the graph decreases without bound. So I can say that as x approaches negative infinity, y does the same thing, it approaches negative infinity. On the right hand side, when you go to the right, the graph increases without bound. This is a cubic function, this is third degree, okay? X times x times x gives you a cubic, okay? And increases without bound. So I can say as x goes to positive infinity, y increases without bound, which means it goes to positive infinity as well. All right, so when you describe the end behavior, you're talking about as x approaches negative or positive infinity. Okay, as x approaches infinity, what happens? You know, y approaches blank, all right? As x approaches negative infinity, y approaches blank. You know, this is what I mean by end behavior. Okay, so you really have to understand the terminology and the vocabulary in the lessons here. Otherwise, you won't be able to answer simple things. And this, overall speaking, is actually quite simple. As long as you study and, you know, devote enough time and energy and use Desmos properly, you should be able to learn these things fairly quickly. As long as you've been through the activities too as well. Some of you guys have not even been to class, and so God help you. But if you've been to class and you've been working through the activities, you should be able to review well enough so that you can go through all of these and really get a hang of the material. And since this is a video, as you guys know, you can go back to the very beginning and review anything you like, all right, to get you guys ready for your last test of the year. Well, actually, the final is the last test of the year. All right, so this is the last section test. All right, so use it effectively, make yourself proud, and I will see you in my next lesson. This is Mr. Ainsworth. I'm out of here. Bye-bye.